I've been working with glass for Saint-Gobain since 1998. Since 2014, I've been working with specification of glass in Sweden and Norway. And since 2018, I've been working more and more on sustainability questions. So today, I want to talk about three different things. First, the operational footprint of buildings, and then to the newer sort of issues of the embodied carbon in buildings. And then finally, I will talk about the need for building simulation to sort of marry the two, the operational and the embodied carbon footprint. So starting with the operational carbon footprint of the glass, it's really been a good trip. If we look at the development, if we look at an existing building like the one described to the left, the light blue area is the operational footprint of an existing building like this one. And the dark blue is the embodied carbon when it was built. So in existing buildings over 60 years, 80% of the carbon footprint, 80% of the total carbon footprint comes from the operation and 20 from the building. And now the ones that we are designing and building at the moment, it's the opposite. So 40% only is operational footprint and 60% is embodied carbon. So how did we improve the operational footprint? It's actually about what's called spectrophotometrics, the art of regulating the energy flow through the glass. So if we look at the energy that we try to control, all of us in here are black bodies or on Earth between minus 50 and plus 100 degrees. If we look at this guy's foot, he will give off low energy radiation, very long wave at slightly under, like 35 degrees if his foot is cold. If he would have been holding a coffee cup, that would be 100 degrees. So that's all those wavelengths are trying to get out to escape the room. And that is the main focus of operational footprint, to prevent the heat from leaving the room. And then we also, I will get back to the overheating things that comes more and more that we've been discussing. And that's a totally different wavelength. The sun has a temperature of over 4,500 degrees, and it emits much shorter wavelengths. So even if over half of it is invisible infrared light, it's totally different. What's trying to get into the room is totally different from what's trying to get out of the room. And that's what we're playing with in our business. So the U value is measuring the heat traveling out of the building. And it travels out in three different ways. It can radiate out through the glass, these long wave radiations. It can convect through the glass, and it can conduct through the glass frame. So if we look at the first thing, the radiation, that is something that has improved a lot. Today we put a coating on the glass that we didn't really 20 years ago. And it reflects back between 97 and 99% of the long wave radiation trying to escape the room. So there we are near perfect. When it comes to the convection, the air gets chilled at the outside of the pane, and it rises on the inside of the pane, and then you get a convection leading the heat out of the room. And that is stopped much more efficiently by a triple glass unit than by a double glass unit, because you get two different convections. And that is especially notable in a leaning, in a roof construction, because there otherwise you have only like 16 millimeters of convection, and if you go to a triple glass, you get much more stability. Finally, looking at the conduction, we need to start looking at window size, because the U value for the glass measures the convection and there's so many things to remember. The convection and the radiation. Whereas the U value for the window also includes the conduction, and the conduction is mainly in the frame area. So in this diagram, here I have a tall and narrow window, and I compare that to a bigger window. And with the same U value of the glass and the same U value of the frame, if I take the tall and narrow, I have a very high U value. But if I increase the size of the window, I get a better U value for the window. So at 2.5 square meters, I'm at 0.8. And that's actually what Norwegian legislation demands. So if we transfer that to the building, we can see that all dividers are like cold bridges or conductors. And that means that the fewer conductors we use, the better the U value will be. So instead of trying to find the perfect material, we need to combine them in a more simple way. To the left is Regionens Hus in Gothenburg, and that is actually a facade that has, with just one window and one spandrel per facade unit, we get a U value of 0.5 for the facade, which is good. If we look at the Axis head office in Lund, on the other side, it has more dividers, and even with good materials, the facade units are at 0.5. Sorry, the first facade is at 0.5. These facade units are at 0.7, and that's just numbers, but we will get up to 0.9 for the facade. And I can relate that to the Swedish legislation that says the newest is that the whole enclosure of the building, the roof, the basement, and the facade can have a maximum U value of 0.5. And that means, if you think about it, the taller the building, the more responsibility on the facade. So if we want to build higher than 8 stories, we cannot use the facade to the left. I see everything mirrored, I'm sorry. That sort of puts a leash on the creativity of architects, which is sad, but we need to think about it. We can also see that the window sizes in the Regionens Hus facade, which is the one to the right for you, is quite small. It's only 30%. And that means that daylight, the light transmission, is getting more and more important. And then it's good news that for standard triple glass unit, low E glass, the ones that I use in my U value calculations, the light transmission has gone up. And how can we get more and more light transmission all the time? Well, actually, it's because trying to prevent heat from leaving the room has nothing to do with the daylight. So by reducing the reflection of the glass and making the coating or the coatings and making them more and more bright, we've been able, since 2014, to improve the light transmission by 7 percentage points, which is really, really good. Now, with the low E coating, we can actually have a higher light transmission than without it. And that is because a glass surface reflects back 4% of the light perpendicular. But if we put a non-reflective coating on it, then it transmits more light. And a non-reflective low E coating will increase light transmission. So going over to the other part of the spectrophotometrics, the solar radiation. That is actually the heat or the energy that reaches the flower inside on this picture. So what hits us from outside. There we've had a very good development over the last 30 years. So we started adding silver to the solar control coatings in 1990. And we get like a spectral curve that takes away the infrared light more than the visible light. And from 2000, we got what's called the SKN coating. So the curve with double silver, the curve was improved. And with the triple silver product that we use today, the only energy that's let into the room by radiation is in the form of visible light. So we've actually managed to design spectral curves to fit the daylight. So on the top right is the E-class low E glass, which transmits basically everything. that is coming from the sun. And then the middle orange curve that shows the Extreme 7033 product, which is in the family that does not transmit anything else than visible light, is the one that has the highest light transmission. And that's why I use it a lot, because to go to a lower energy transmission or G value, we have to kill daylight. And we can't do that with the small window sizes we have. So I think we need to find other ways of doing that with dynamic facades. So yeah, like I said, we're cutting out the daylight. And with such a glass, that is how I could sit at this interview with 26 degrees outside, the sun shining at me. And I was a little sweaty at the throat, but it was very comfortable for the rest of me. So that's what solar control glass can do. And with these spectral curves, we get better views to the outside as well. Here we can see that the window to the right is open and the window to the left is closed. And there is no real visible difference in the transmission. That is with low E glass, and that is for the eye is very nice. And also we can see that for the solar control glass, this is the Extreme 7033, and there is a door open, and you can see that there is a 30 percentage points difference in light transmission, but the colors are there, which is great. And this has sort of been able to really push down the operational footprint. And now we're coming into the building integrated photovoltaics, which is like on this wall, where you can actually get a plus energy building when it comes to operational footprint. But we still use the monocrystalline solar cells, and they have a very high embodied carbon footprint, which leads us on to the next area, the embodied carbon footprint. Well, in the conclusion, glass development and building integrated photovoltaics helps really reduce the operational footprint. So going over to the embodied carbon footprint, I show the same slide again. We're actually increasing a bit the embodied carbon to get the low operational footprint. And when it comes to glass, I've been talking about coatings now forever, it seems. Only 2% of the carbon footprint of glass comes from the coating. So we really need to use the coatings as much as you can. And we need to reduce the number of kilos of glass that we use. So you can see here that float process emissions, float electricity, that's 85% of the carbon footprint, so that's where we need to go. And there we have some issues recent, especially the strive for acoustic comfort. If we look at, you don't have to read all the figures here, but the blue arrows on top represent better and better sound reduction in the glass. And the green, yellow, and red arrows, they represent the weight of those glasses. So we go from 46 kilos to 76 kilos per square meter. And the kilos are driving the carbon footprint. So we need to be really careful in how to set the acoustic comfort in our buildings, not to overuse the carbon footprint. This is captured by the EPDs. We've been talking about LCAs, I saw. And the EPDs, they capture this relation, not for every glass type yet, but our product calculator by this Christmas will take any glass combination and give an EPD for it, which is good, because then we can get the carbon footprint correctly for the facade. What's not captured is the optimization, that a piece of glass is usually 3 by 6 meters, the raw material. And if we set in a facade the window sizes based on the carrying structure, we might really lose out on the cutting waste. And then we don't use the material as well as we can. So we need to go do something about the glass, especially because in 40 to 50 years, we will not have anything left of the quality of sand that we need to produce glass. So we need to start recycling. And how does it look today? Well, today we have 30% recycled material in our float. But 20% of that comes from the float lines themselves, and 10% is the cutting waste that comes back to the floats. So less than 1% is what's called post-consumer cullet, so end-of-life cullet. So we basically don't use anything of the old glass, and we need to start doing that. And if we look at today, this is a Swedish slide, but plan glass means flat glass, and förpackningsglas means basically bottles. And then you have mineral wool. What we do today is often downgrading. We take the glass and we make glass wool, and then we can never make it into glass again. So to truly recycle the glass, we need to make it into circular use. So that's why I say the circular use of flat glass, not to let it become something that can never be flat glass again. And that is a very important step to getting zero carbon glass, because that's what we need by 2045 or 2050. And this is a calculation that's been done by a Swedish consultancy for the Swedish glass business. And it has the different steps on how to reach zero carbon glass. And the top light blue is transportation. And then the dark blue is the optimization that I just talked about. That's not captured by the EPDs. The orange is to bring 20% of the raw material to be from end-of-life glass. So that is actually the single most important step, and it's the one thing that we can influence. Because green electricity for glass processors, or green electricity for floats like the yellow, or hydrogen for melting glass like the green, or the gray to get the soda from zero energy sources, we can't do anything about that. So how does it look in Sweden that we always say is so great? Well, I visited Växjö in a research project, and it turns out that for bottles we're good. 97% is recycled. Windows in Växjö, the windows were dismantled. You broke the frames, you broke the glass out of the frame, put the glass to a landfill and burnt the wooden frame. So most of the glass goes to landfill from end of life, and what is not is downgraded. And what do we lose out on by that? Well, the 35,000 tons we're talking about for Sweden could bring a net saving of 10,000 tons of CO2 and 40,000 tons of virgin material, because you use 1,200 kilos of virgin material for 1,000 kilos of glass, but 1,000 kilos of cullet for 1,000 kilos of glass. So we've actually been able to start recycling at like a test stage for 2 projects in Sweden. The first one was the IKEA, the round building is IKEA in Kungens Kurva, the biggest IKEA warehouse in the world, where the old glass facade was replaced by a new, and we tried to recycle the old glass. It went so-so. I will get back to that. The other one, the next one, that was only 9 tons. And the next one is over 100 tons. It's the old SAS headquarters north of Stockholm, where the old atrium to the right was replaced. And here I need to actually show a couple of pictures of how beautiful our solar control glass can look. This is the Extreme 7033 in these, well, I'm not supposed to point, but in these atriums is solar control glass. And you can't really see that it's solar control glass. But in the replacement from just basic float, the U value went from 2.7 to 1.0, and the energy transmission going in went from almost 90% to almost 30%. And that was a huge improvement for the indoor climate. What to think about when recycling glass? Why are we not doing it? Well, the first step is actually quite simple. If you're involved in a project which involves destruction or renovation, you can say that if the windows are taken out in one piece and put standing on a stillage that can be transported somewhere, then you've done your bit. Because as soon as the glass is broken, it gets contaminated. You have the aluminum frames, for instance, if they are broken in the insulating glass units, they give off small fractions of aluminum that ends up in the float, that ends up as enclosures, and then you have to scrap the glass. So the case study, getting back to IKEA in Kungens Kurva, the big issue there was the fire escape, because there were fire glass there. There was an E30 demand. And we did put big crosses on those glasses because they're sort of like poison to the float tank. This was the only way to see if you didn't put crosses. It says shot on the ones to the left and not on the ones to the right. That shows that it's a glass product that's actually not glass because it has a much higher melting point. And what happened was we put it in 2 different containers, and somebody saw it and said that, there are ridiculously low amounts of glass in that container. Let's put it together with the rest and then ship it for better shipment. That glass did not reach the float tank in Torgau, but another batch of like 3-4 square meters of that did reach the 2,000 tons of glass melt here. And these are the errors of a standard 24-hour period. And when 3 square meters of fiberglass dropped in the tank, the errors just exploded. And 6 days later, we still had problems. So we lost 634 tons of glass. It cost 230,000 euros just for one mistake. So that's why it's a tricky process. And that's why I'm really proud that our partner for these 2 projects, which is Ragn-Sells, they decided to invest heavily into making end-of-waste glass, as we say, an end-of-waste product, to take the old windows and to turn them into raw material for glass production. It's called end-of-waste. And we're in a partnership on this, and from the second quarter next year, we will be up and running in the big cities in Sweden. And since Ragn-Sells is also in Estonia, I hope that it will reach us quite soon. So, the focus is starting to shift from the operational footprint of the glass to the embodied carbon. And we need to balance those 2. And that's difficult, and that's why we need building simulation. If we look at the Swedish legislation, the actions for the Energy Performance of Buildings Directive, we see that we focus actually more than before on the good access to daylight. So we need high light transmission in our facades. But we have ever stricter demands on energy consumption, meaning smaller windows and less energy allowed to flow through them from the outside. And we also have an old legislation, 20 years now, saying that the solution needs to be proven in a building simulation software. So we use that a lot in Sweden. The Ida Ice by Equa Simulation is the one mostly used. The news that's coming next year is the carbon footprint, not of the whole building, but of the structure, the inner walls, and the facades, needs to be declared to get a building permit starting next year. You can do it with generic values, of course, but Saint-Gobain is striving to facilitate the possibility to use real values. And then maybe a year after that, the solar heat gain, how much heat comes in per square meter there divided by the floor surface, might become part of legislation. Probably not, but over temperatures inside buildings, that's where the legislators are looking for a way of regulating that without, sub-optimization. And it's important to do early simulations in these stages, because this is probably a graph that you've seen before. The yellow is the effectiveness of a change. If you take a decision very early on the drawing stage, on the early stage, to make a change, it has a very high efficiency. And the blue line then, the bluish, greenish, is the cost of such a change. So at the earliest stage possible, the cost is almost 0. It's a few hours of work. Whereas when you get to when the building is already built, if it's too hot, you can maybe hang a curtain, which is probably expensive and not efficient. So you need to look at your house in early stages. And that's what's done in a Swedish freeware, actually called ESPO, Early Stage Building Optimization. They are working heavily on making templates for architects for what's called simple box modeling. And that is when you have a facade in a hotel or a hospital or an office where most of the facades look the same, the facade part. There you can take a small piece of it and really analyze it carefully and look not only at the glass, but also at what kind of outside or inside shader you can use, and what ventilation system and cooling system. And they're looking to make templates that sort of balances that for different solutions. And then also to actually get the carbon footprint out of those. So then comes the question, a little shaky move here, but can daylight rules increase the carbon footprint of buildings? I said before that the coatings can let through enormous amounts of light, but if you use the 75%, which is like the top level for our low E, well, I said 77, but 75 is when you count some sound reduction and stuff. If you use that, you need an outside shader if you're in the north, if you're not in the north, if you're in the south, east, or west. And maybe you want to protect that outside shader by building a double skin or a hybrid window. And then with the extra glass, you lose 10 percentage point of light. But also, with the extra glass, you add kilos of glass, adding carbon footprint. So your facade decision will have a very big impact on the carbon footprint of the building. So if we look to the right, the Regionens Hus in Gothenburg, that I won a prize for, that's why I'm showing it all the time. And it's also because it's debated. Some people think it's beautiful, others think it's ugly. It has solar control glass with an inside shader, an efficient, and a product calculation for the system. And yes, the building works, and it has, you can see that, you can sense that it has a low carbon footprint. If you instead have outside shaders like the building in the middle in Vilnius, then you go to a bigger carbon footprint because of all these installations. And if you have a double skin facade, you have a lot of openable units inside, and then you have an extra glass, so you add carbon footprint. So you need to think about that in the design phase and choose the lowest carbon footprint. So I use 4 glass types for most facades. This is sort of commercial-ish or a message from your sponsors. But still, it's relevant to know that I base my decisions on light transmission. Then you have to fix the rest afterwards. So if you want 75% light transmission, that's fine. That can be found. But you get a very high G value, energy transmission. And you need to get it down to what's called a G total. In Sweden, we have the Miljöbyggnad rules talks about the G system, which I like using because then you talk about Jesus. But now we talk about G tot, which is a lot more boring. Anyway, with an outside shader, we can get the low E glass down to 0.15 to 0.10, depending on how open we have the fabric, how much view to the outside we allow. The next one is if you use the SKN 183, which is our brightest solar control glass. So it has 67% light transmission, can be made stable on triple glass. And the total G value if you use an inside shader, it can drop to below 0.20, which is what we need in an open office landscape. And with an outside shader, it can go between lower than 0.05, which is what we might need in a cell office with a big window. So it's a flexible glass. And then we have the Extreme 7033 that I think I've mentioned before somehow. You go down from 67 to 63% light transmission. But this glass, in the analysis that we make in the building simulation softwares, it's a lot more efficient. So we actually get down to 0.15, which can be enough for most applications in an office building. We can get it down to 0.11, but then we're talking about a very theoretical calculation of the sun hitting us perpendicular. Because with an inside shader, when it bounces straight out again, that's the optimum. If it bounces on the shader and into the frame, it's not so efficient. So depending on if you need it for thermal comfort or not, then you can use this glass. This application normally works for everything if you have cooling. But in schools in Sweden, we don't have cooling, so then you have to really think again. Finally, if you don't want any shader, I said below 20% is what's okay for an open office landscape. And then I have the extreme 5022, which is a bit more darkish, a bit more bluish, but it brings you there without any shader. But then you're down to like 40% light transmission. So in rehearsal, 4 glass types. 1 for outside shaders or north position, 1 for either inside or outside shaders and other positions, and then 1 that's very efficient, more expensive, but very efficient with inside shaders. And then finally, a glass that you can use without shaders. So depending on the application, you can choose from that toolbox. That's how I usually do my specification. Of course, there is a lot more to learn, a lot more to study. And I've written a book about it. It's 75 pages, it's in English, it's quite heavy, but it gives you the opportunity to really learn a lot more on this topic. You can, if you're not in the room and can get it physically, it's actually pretty cool. You Google my name nowadays, Oskar Storm, and then you come to my booklet. So that is my biggest achievement, aside from being working with getting the carbon footprint, or no, getting this partnership with Ragn-Sells to start recycling glass for real. So thank you very much, and now I'm open for questions.
Thank you, Oskar. It was really interesting.
Thanks.
Before we go to questions, I will try to make a really short summary in Estonian. So
Good luck.
Hold on. Tere ka minu poolt, olen Agneta Jääpere, töötan samuti Saint-Gobainis ja samamoodi nagu Oskar, siis vastutan Eesti ja Soome turu arhitektuursete projektide spetsifikatsiooni eest. Et siis lugu, mis Oskar rääkis meile lühidalt kokku võtta eesti keeles 2 minutiga, on paras väljakutse, aga ma teen endast parima. Ehk siis see peamine sõnum esimeses osas oli tal see, et me oleme hästi palju tähelepanu täna pööranud oma toodete soojapidavusele, valguse läbilaskvusele ja päikese kaitsele. Ehk need on need põhi 3 komponenti, millega me oma spetsifikatsioone täna teeme. Aga sealt edasi tuleb tähelepanu pöörata ka nii-öelda siis taaskasutusele, mille peale mõningal määral juba mõeldakse. On olemas siis toote toimivusdeklaratsioonid ehk siis EPD-d, samamoodi olelusringi hindamisaktid, LCA-d ja sealt edasi ka ju hoonetele väljastatavad sertifikaadid, mis siis annavad jätkusuutlikkuse nii-öelda hinnangu, et kui hea ja tõhus teie hoone on. Et nende teemadega ma loodan siiralt, et ka Eestis järjest rohkem ja rohkem tegeletakse ja pööratakse ka tähelepanu siis materjalide taaskasutusele. Et Klaasi puhul me täna proovime nii palju kui võimalik siis toorklaasi tootes seda klaasi taaskasutada, aga see on liialt väike, et saavutada neid eesmärke, mis on ette antud. Et see tähendab seda, et me peame leidma uusi võimalusi, kuidas ära kasutada ka juba kasutatud klaasi. Et mitte võtta seda klaasi ja teha tast nii-öelda lihtsalt mingisugune täide kuskil pinnases, vaid et võtta see klaas ja anda talle uus elu. Sest klaas tegelikult oma olemuselt on taaskasutatav oma kvaliteeti kaotamata. Et see on nagu suurepärane materjal, mida nagu korduvalt ja korduvalt saab taaskasutada, kui seda õigesti teha. Loomulikult see float'i näide, mis Oskar tõi, kus oli IKEA aknad, siis, kus osaliselt olid tuletõkkeklaasid ja osaliselt olid tavaklaasid, et kui vale klaas satub taaskasutusse, siis meie float'i tehases on väga-väga suur probleem. Et sellepärast tuleb hästi hoolikalt seda sorteerida ja väga targalt taaskasutada. Nüüd tulles selle viimase teema juurde, et kuidas Rootsis neid hooneid nagu arvutatakse või kuidas tehakse neid otsuseid, et millises projekteerimisetapis teha juba see õige valik, et hoone oleks jätkusuutlik ja et hoone annaks võimalikult vähest keskkonnamõju. Siis ma arvan, et Eestil on väga palju sellest õppida ja teha neid õigeid otsuseid võimalikult varajases staadiumis. Ehk alustades juba eelprojektiga tuleks hinnata, milliseid tooteid kasutatakse, kas neil toodetel on kõikidel sertifikaadid olemas, et hiljem see hoone oleks tõeliselt nagu keskkonnasõbralik. Nii, ma arvan, et ma sain laias laastus hakkama. Kui kellelgi koha peal või online'is on küsimusi, siis me Oskariga hea meelega vastame neile edaspidi. Meie kontaktid lähevad hiljem ka välja ja kõik need materjalid, kaasa arvatud Oskari booklet on all olemas, on internetist leitav ja siis ma annaksin nüüd sõna Ainarile. Ainar küsib ühe küsimuse ka veel. So, thank you once more and Ainar will ask you one question.
Ise küsida.
Really? Okay. I will take the honor. I will ask myself. Would you please tell us, is there any kind of good tool how to calculate the facade carbon footprint?
Yeah, well, a unitized facade is tri-dimensional, so it's difficult. You have to get it from the facade maker, from like the glass system maker and the glass processor. But if you think about a hole-in-the-wall facade and you think about this simple box modeling, we're actually putting all our Saint-Gobain walls. It's only been glass and shader material and ventilation and cooling before in that tool. But now Saint-Gobain in Sweden is putting the different isover wall types like cross-laminated wood or concrete structure. They're putting all the LCA documentations, the EPD, into the tool of Espo. And that means that within a year, we should be able to see 4 standard facades like this, hole in the wall. We should be able to get a carbon footprint directly from the building simulation, which is when you need it, in the early stage.